going over tables. Okay. I think I did this right. All right, so we're gonna have an intensive little review, and then we'll go over the motion problems. Okay, so when you're just given a table of values, one of the very first things they're going to ask you to do is to approximate the derivative at a particular value. And to approximate the derivative, what formula are we going to use? What formula? Yes, slope formula. And you want to make sure you're using 2 points either at A or near A. Don't pick them somewhere far away. It's going to cause problems for Justin. I'm glad you came in. Okay, now, so we'll use the slope formula, and to find the units of the derivative, like in this case it could be dt, or whatever. What are you going to do to the units of y and the units of x? What operation to find the units of the derivative? Change in something over, change for something else. Units of the derivative. Yep. Yeah, and when you say over, what operation is that? Yeah, division. So you're going to divide to get the units of your derivative. You're approximating a derivative, and to get the units, you divide the units of y, or whatever it is, by the units of x. So let's do an example. So let's say we're given a chart of values. We're told the velocity at particular times. We're given the velocity for certain times. And they ask us to approximate the acceleration when t equals 8. And we know acceleration is the derivative of velocity. So if we want to approximate the derivative of velocity at t equals 8, we're going to use the slope formula. And what points do you think we should use? What times? 6 and 9. Now, because 8's in there, so you really have no choice. That's the best one. Okay? If it was 9, then you could have picked, 6, 12, 6, 9, 12. But it really is no. So now, let's just be, so we're approximating dv dt. That's what acceleration is. We're approximating it with the change in velocity over the change in time. So we picked points. Tell me what to write for the numerator. I don't care which one you start at. You know? Do we want to put the change in time in the numerator? Okay. Okay, so we'll do 7 minus 8, and then you have to do 9 minus 6. So what does that give us? Negative 1/3. Now, as far as the units go, we have to take the units of velocity and divide them by the units of the denominator, units of time. What would that give us? So the units of the numerator, miles per hour, and we got to divide them by the units of the denominator. What do you get if you take miles per hour and you divide by hours? Miles per hour squared. Right? If you guys like that whole keep change flip. So the units would be miles per hour squared. That makes sense for the units of acceleration, right? So that's the first thing you got to do. You got to be able to approximate everything with table problems. It's approximate. The next thing you want to be able to approximate is the definite integral. If you're asked to approximate the definite integral, there are only 2 shapes we've ever worked with to approximate the area under the curve. What are those 2 shapes we've worked with? What if we approximated the area under the curve? Trapezoids and rectangles. Now, when you're looking to get the units for the definite integral or antiderivative, what are we going to do with the units of f of x and the units of the differential? these units. With the derivative, we divided, right? Here, we're going to multiply. So we're going to multiply. You know, and it's not anything you have to memorize. Just look at it and see. You know, you're multiplying. So you multiply units. With the derivative, change of y over change of x is you're dividing. So you divide for the units. Now, if they want you to use rectangles, they're going to say either left Riemann sum, midpoint Riemann sum, right Riemann sum. You see Riemann sum, you think rectangles. If the widths are all the same, of all your rectangles, if you see that those points that they give you are evenly spaced, then you can just pull the width out and multiply by the sum of the heights, because every rectangle has an area width times height. So if the widths are the same, you can factor out the width and multiply by the sum of the heights. And remember how we would get the width? If you have an interval from 0 to 10 and you're trying to fit in 5 rectangles, what's the width of each one? 2, right? You take 10, b minus a over 10 to get the width. But with the charts, they usually tell you to use the intervals that they give you. But yeah, you can factor out the width if they're all the same. But if they're not all the same, if the widths are all different, you see those points, they're not evenly spaced, then you have to find the area of each rectangle separately. Just add them all up. Okay? Width times height for the first rectangle, width times height for the second rectangle, etc. Let's try it. Yes. Yeah, you use the y coordinate at the midpoint of each subinterval. They can never ask you to use as many rectangles for a midpoint, so you always want to watch out for that. We're going to do an example right now. I'll show you. For our first example, you're given the velocity at particular times, and you notice that these times are all evenly spaced. You see that? So we will be able to factor out the width for a rectangle. So we want to approximate the definite integral of using rectangles first, using the left-hand Riemann sum with the 6 rectangles. So what is the width of each rectangle going to be for approximating the definite integral from 0 to 18? It'll be 3, right? 18 minus 0 over 6 is 3. And because these are all nice and evenly spaced, we can factor that out. And then just multiply that by the sum of the heights. Now the heights of your rectangles, those are your velocity values, they're your y values. But there are 7 of them. You got to make sure you choose the correct ones. So for a left-hand Riemann sum, what would be the height of my very first rectangle? 2. You use the one on the left, right? Because the times are going from 0 to 3. So 2. And then for the second one, 6. And I'm going to keep going until I get to it. So you get to this one. I know you're just not going to use the last one. So 2 plus 6 plus 5 plus 3 plus 1 plus 2. So we just add up all those heights, multiply by the 3. Good. And what do we get? Do I know this? That sounds good. 57. What would the units be? Because we're approximating a definite integral. The units be, yes, Karen? Just miles, because when you multiply miles per hour times hour, you get miles. Which makes sense, because when you integrate velocity, we said yesterday, you get the total displacement, which we measured in miles. Now we can address your question. It says, use a midpoint Riemann sum rectangle approximation method. But you notice we can only use 3. One thing I want to tell you guys, never make up a number given a table problem. You don't just say, oh, it's somewhere in the middle of these, and I'll just say it's 5.5 or whatever. If you're making up a number to use, you're not doing it right. You have to only use the points that are given. So if I'm using 3 rectangles, what's the width of each rectangle? 6. So now I got to figure out what are the 3 heights. Because if I only have 3 rectangles, I should only have 3 heights. So for the first rectangle, times go from 0 to 6. Whose y coordinate do you want to use for the height of the first one? Yeah, you want to use the y coordinate 3, which is 6. So 6 will be the height of the first rectangle. Okay? The second rectangle, the times go from 6 to 12. Right? So whose y coordinate do you want to use now? The 9, right? And that is 3. And then in the third and final rectangle, what are we going to use for the height? 2. So we add up the heights, multiply by 6, and what do we get? 66. And again, because we're approximating a definite integral, we multiply the units, and that gives us miles. All right, one more. Here's a right hand. 6 of them, so what's the width of each one? 3. All right, let's rattle off those heights. 6 plus 5 plus 3 plus 1 plus 2 plus 4. What does this approximation give us? 63? Love that. You guys just have these numbers for me. Excellent service. Okay, so we only factor out the width if it's going to be the same for all of them. And for that to happen with the table problem, the points have to be evenly spaced. Okay? Now, they could also ask you to approximate the definite integral using trapezoids. And again, if they're evenly spaced, okay, um, you can factor out the half, because that's always going to be a common factor. But you can also figure out what we call the height of our trapezoid. It's the same as the width of the rectangle, at b minus a over n. So you will be able to factor out the half and the change in x. Okay. But then you're still going to have left for each trapezoid the sum of the bases. The bases are the y's. When you have the same height for each one and you factor it out, remember what happens? All the bases in the interior get doubled. You have 2 of them. So when you have the height, or like the width of your rectangle is the same for all of them, you factor out the half times your change in x. You take one of the first y coordinates plus 2 times the sum of all the interior y values, and then one of the last. You only do that doubling the middle ones if you have a common height. So let's try this one. So these are evenly spaced. So we are going to be able to pull out the half. And we're using 6 of them again. So the b minus a over n, or the, what is that going to be? When I say the height, I'm talking about this value here. The height. You know, when you got a trapezoid, the bases are parallel sides. Yes, that's 3. So you have 1/2 times 3. Now, we're going to take the sum of the bases, remembering that the internal bases are going to be used twice. So, the first base is 2. Write that down. But then we want to double the sum of all the interior bases. So, plus 2 times 6, I heard it, plus 5. Keep going until I stop doubling. So now, stop the doubling, but then we still have to remember to write plus 4, that last y. So again, you can only do this when each of the trapezoids has the same height, when the points are evenly spaced. I don't know what this is going to be. 60? Thanks. And again, we're approximating a definite integral, same units, miles. Sometimes in this world, points are not evenly spaced. Now, suppose you're given, in this case, 7 points. But you see they're not evenly spaced. One, two. Then you're going to have to do each rectangle or each trapezoid separately. So we first want to approximate the definite integral from 0 to 12. And they would say, I didn't write it on here, using the indicated subintervals, using the points you've got. Okay. Let's first approximate the definite integral with the left-hand Riemann sum. So remember, we're going to get width times height plus width times height for each rectangle. The first rectangle, what's the width? The times go from 0 to 1, so the width would be 1. Now, which y are we going to use for the height? Yeah, the one at 0, so that'd be 1. So the area of my first rectangle, if I'm using a left hand, would be 1 times 1. Right. What about my second rectangle? What's the width? 2 times 3. Yeah. So 2 times 3. 2 is the width. That's like the difference in your independent variable. And the height is your y, or dependent variable. All right, we got 2 times 3. We got to keep going. Next one. Plus 2 times 0. Nice. Okay. Next one. 1 times 2. Next one. 3 times 4. Plus 3 times 5. So 36. 36. Units again, we multiply. So let's do that. Now, if you change the directions from left to right, it's only going to change the heights. The widths are all going to be the same. All right, let's go through it. We'll do this one. So for the first rectangle, it's 1 times 3. And then the next one, 2 times 0. Plus 2 times 2. Plus 1 times 4. Plus 3 times 5. And then 3 times 10. Oh, I don't know why I put the 36 just here. That was for just the left hand. All right, that was the left hand. Now, what is this one going to be? 56. So this, the right-hand Riemann sum would be 56, and that would be our, if we said the definite integral was, we'd say it's approximately equal to 56. Okay. I know what you're thinking. Oh, I hope we get to do a trapezoid with unequal subintervals. Yep, I think we are going to now. All right. So now we have these points. They're not evenly spaced. We want to approximate the definite integral with trapezoids. Now remember, each trapezoid has an area of 1/2 the height times the sum of the bases. If the heights are all different, the only thing you can factor out is the half. For each trapezoid, you're still going to have to take the height, that's like the difference in the x's, times the sum of the bases. So you're going to have, in the parentheses, you're going to have height times the sum of the bases, plus height times the sum of the bases for each one. Just don't forget the half. Kids, you forget the half. Alright, so for the first trapezoid, what's the height? 1. Now what do I write for the sum of the bases? 1 plus 3. Nice. Second one. 2 times 3 plus 0. Next one. 2 times 2. Nice. Plus 3. Oh no, I'm out of room and I'm not done. Plus. Oh. Wow. That's right. All right, so the definite integral, I think that is right. 0 to 12 is approximately equal to 46 miles if we use trapezoids. Not so bad, right? What do you like better, equal or unequal? Oh, that was the right answer. Good. Do we need this one here? And those are the big things. Approximating the derivative with the slope formula or the definite integral with rectangles or trapezoids, that's the big thing. There are three other little things I'm going to mention. The third thing they can ask you to approximate is the average value of a function. Now, if they ask you to approximate the average value of a function, the 1 over b minus a, you're going to be able to do that, right? Let's say approximate the value of whatever this function is over the interval. But remember, it's 1 over b minus a times the definite integral from a to b. You're just going to use whatever number you got using rectangles or trapezoids for this part. So you just take your approximation and multiply it by 1 over b minus a, or divide by b minus a. That's how you approximate the average value of a function over an interval. Now, here's our little example. So it says, in example D, use LRAM, the LRAM approximation from the problem before, to approximate the average velocity on the interval from 0 to 12. So what's my little fraction out front? 1 over 12 minus 0. Okay. Do you remember what we got for the LRAM approximation in that last one? What is it? 36? Oh, that works out nicely. So what do we get? 3. Now the units for, and this was approximate the average velocity. Okay, so we're approximating it. The units should be the same as the velocity units. Oh no, I gotta pause. Back to this. So yeah, the units would be the same as the units for velocity, the average velocity, right? So what was that? Was that miles per hour? Miles per hour? Yeah. Because this is miles and this was hours. So miles. Okay, average rate of change. You actually will be able to find if they give you a table. You won't have to approximate it because remember the average rate of change of a function? It's just the change in y's over change in x's. If they've given you a table of values, that's no problem. So if you look at this, our last table, it says find the average rate of change of the velocity in the interval from 0 to 12. Average rate of change of the velocity, not the average velocity. So that's what you just do. The velocity at 12 minus the velocity at 0. That's the same as the average acceleration, because rate of change of velocity is acceleration. I don't remember the numbers. What was v of 12? 10 minus v of 0. So 10 minus 1 over 12. 3/4. Like that reducing. And the units would be the units of velocity over the units of time. So that would be miles per hour squared. Because it's the change in velocity or change in time. All right, one more thing they can ask you to do. I promise. They can ask you if you got an approximation for the definite integral. They would have to give you some kind of information, like they have to tell you that the first derivative was positive, so you would know it was increasing, or something so you know it was increasing or decreasing, or concave up or down. But if they gave you the extra information, and if you have a function that's increasing, and you've used a left-hand Riemann sum, will that be under or over? That'll be under, right? If you're using under. If the function is decreasing, and you use the left-hand Riemann sum, that's over. If your function is concave up, and you've used trapezoids, over. And if your function is concave down and you use these trapezoids, your approximation will be under. So when you try these problems tonight, try to keep all this in mind, because I've tried to cover so you can approximate derivatives with the slope formula, anti-definite integrals with rectangles or trapezoids, and the other stuff. All right, let's look at some of these homework problems. We'll have to go over some more of them tomorrow. But the first one and the last one were calculator. The middle one wasn't. I wanted to make sure that you were using, and I gave you the answers somewhere in that big book I gave you today, using your calculator to your advantage. When they give you a calculator question, you really should enter those right into your calculator. Now, I put the velocity in y1 and acceleration in y2. What I didn't do originally was put parentheses all around something. This, the sign, and that totally messed me up. So if you're not getting the right answers, check that you did that. Use those right there. But when you have a calculator question like that, it's just really knowing the concepts after that. In A, they ask you if the particle's speed is increasing or decreasing at t equals 5.5. You don't have to go back and type in the equations and plug in 5.5. If you've entered them in y1 and y2, you just write on your home screen, y1 of 5.5, that's negative something. y2 of 5.5, that's also negative. So if the velocity and the acceleration are both negative, is it speeding up or slowing down? Speeding up, same sign, yep. Okay, so when you enter, let me just go back to where you entered it. Are you in radian mode? You are, for sure? Okay, so did you get either one of those numbers when you tried this? Okay. So the 2 sign, then you got to open the parentheses. You don't need parentheses here. Because if you don't want to, did you close the parentheses? You opened parentheses after the 2 and closed them after the 1? Okay, what, you opened them after the 2 and closed them after here? Because you don't need a parenthesis after the 2. Yeah. Yes. Got it? Okay. So you're opening another one here. But then it probably is going to keep doing, you're probably undoing this one. I'm just wondering if you keep taking the sign all the way, including the +1. If you take the sign of, oh, you never closed it? If you didn't close, after the 4. So it's like you put the e to the x over 4 in an extra set of parentheses. But the thing is, with that first one, you want to just see if they have the same signs. And once you've entered your function correctly in y1 and y2, don't risk entering it in wrong again. For B, they asked you to find the average velocity. You're given the velocity. So you just have to, that's just 1/6 the definite integral. And on your calculator, you just do 1/6 math 9. Don't enter the velocity again, just type y1, Barr's function, right? 0 to 6. You don't write this on your paper, you just write this on your paper, equals 1.949. Questions for that? The next one, they asked you total distance. Total distance, as far as your work goes, remember distance, you don't just integrate velocity. What do you got to do to, because that'll just give you displacement. Absolute value. So the only work you'd have to show is that. Then equals this answer. You have a calculator. Getting total distance is easy. Just enter it in. Okay. is pretty interesting. First of all, always take notice when they give you an interval for a graph. That's your x min and your x max. All right, you always want to make sure you're graphing on the right for the right x min and x max. You always want to set your window. So they want you to see when it changes. It tells you it changes direction once. Now you have to know it changes direction when the velocity changes sign. So what you want to do is just graph the velocity. So what I did, I turned off the acceleration. I went to its equal sign, hit enter, so it's no longer highlighted. Now it won't graph it. So it only will graph my velocity. And I can see where it crosses. You have to, don't just approximate where it crosses. Use the calc menu, option 2, 0, to get that value. And when you get a value, why not just store it in A? Take that value, 5.195, whatever, store it in alpha A. If you write it on your paper once, you can use it later. Yep. Once you get it, like you're in your 0 screen, you leave the screen, second quit, and then hit store alpha A, enter. The store key is like right over, it's to the left, like on the bottom, it's stow. Yep. Oh, so they want you to find the position at time A. They gave us earlier in the problem the position at time 0 is 2. So we take the position at time 0 plus the change in position by integrating the velocity, because that's the derivative from 0 to A. In my calculator, all I have to do is 2 plus math 9 of y1, comma x, comma 0, comma A. Oh, it got cut off a little bit. And then that'll give you the 14.13, whatever, 5. But I want to make sure you can, so we can really use the calculator to our advantage. And sometimes you don't have these. I know I just said that pretty quickly though, but do you see how we got when it changed direction? Where the velocity crossed, getting to 0, we stored it, and then they want to know its position at that time. Yep. The one that was tough, and I'll probably just get to part A, was the second one. The whole question bother you? They give you the velocity in an equation. The times go from 0 to 12. Guys, if t goes from 0 to 12, what is this whole angle pi over 6 go? Pi over 6t between? If t is a number between 0 and 12, what is pi over 6 times t going to be between? 0 and 2 pi. So we're talking about an angle that's going from 0 to 2 pi. And the first thing they ask us, I think, is when is it moving left? Well, moving left is when the velocity is negative. Okay? So you want to know when is the velocity negative. The velocity is the cosine of this angle. When is the cosine of an angle negative? When the angle is between 90 and, not 180, 270. So when the angle is between pi over 2 and 3 pi over 2, right? So when the angle pi over 6t is in between, well, it'll be negative, I don't want to equals. Oops, we'll have to continue this one. I definitely want to do this one. Pi over 2. We'll solve for t. You can do it. Multiply through by 6. Divide by pi. But try the table problems, and we'll try to get caught up with this tomorrow.